Very good morning to all of you. Today we are going to learn the application of first order differential equations, on the Newton law of cooling. Suppose that T, where the capital T is actually temperature of an object at time, the lowercase t is the time t. The object is heated up to T naught Celsius at T equal to 0 and is placed in the surrounding of Ts in the surrounding temperature, which is less than T naught. According to Newton's law of cooling, the temperature of the object changes at a rate proportional to the difference between the temperature of the objects and the temperature of the surrounding. If you have for example, you have a hot coffee, and then you put it to a room temperature, it will cool down to the room temperature. So that's why what the Newton law of cooling says that the rate of change of the hot coffee or hot object, rate of change, that's why you have d dt, where the capital T is temperature. So d cap T dt is proportional. That's why this is a symbol of proportional, of the difference of the temperature of the hot object with its surrounding temperature. That's why dt dt, proportional to T minus Ts. In the initially you have, the object is hot. After you put it at room temperature as actually your Ts is the cool down, cool down to the room temperature. Since the temperature is decreasing, therefore we use a negative K. In the proportional symbol, if we change it to equal, because the temperature is decreasing, we use it equal to negative K. If you see the equation is positive K, also no problem, because if you put it as negative K, when you calculate it later on, the K value will be positive. So that you still have a negative value. If we write here equal to positive K, later on when you calculate the K, the value will become negative. So it doesn't matter whether your K is positive or negative, but normally people will put it dt equal to negative K. So if negative K, it shows that later on when you calculate, K will be positive. If positive K, after you calculate it, the value of K will be negative. The temperature Tt is obtained from the differential equation. Meaning we got here, this becomes the first order differential equation, which is means the Newton law of cooling says that the rate of change of the temperature of a hot object dt equal to negative K. The temperature of the object, with the different with the room temperature, negative K bracket T minus Ts. You want to find the temperature T here, capital T, and then since that you want to find where the Ts is actually room surrounding temperature or room temperature is a constant value. So this one, where the K is also constant, hence K will be easy. We solve it using separable equation. It will be easy. We solve it using separable equation. So we bring the whole term here, T minus Ts, to left hand side. And then dt bring to right hand side, and then we integrate both hand side. So you have the integral d capital T over T minus Ts equal to negative integral of K dt. Now we integrate left hand side, we have a ln, integrate 1 over T minus Ts, where the Ts is a constant value because surrounding temperature or room temperature. Respect to d capital T, we get ln T minus Ts equal to negative kT plus C. Negative kT plus C. And then, okay, ln is log base e, hence t minus ts is equal to exponent negative kt plus c, where is equal to exponent negative kt plus, multiply exponent c and let the exponent c become a, hence is equal to a exponent negative kt. So with the initial condition t equal to t naught, and when time t equal to 0 is substituted, then you can calculate for a. So you have here. Then later on substitute when t equal to 0. So exponent 0 we have 1. Hence we get this is equal to a. When time t equal to 0, temperature is T naught. So you got A is actually T naught minus Ts. So you plug in the A value here. Plug in the A is actually T naught minus Ts. Then bring the the minus Ts to right hand side. So the temperature of the hot object T will be equal to Ts plus, this is actually the A, exponent negative Kt. For example, 1. It takes 20 minutes to cool an object from 80 Celsius to 50 Celsius. If the temperature of the room is 10 Celsius, so mean this is actually the Ts. Ts is equal to 10 Celsius. Find the time needed to cool the object. From this equation, you can either you solve the K or you want to find the T. The temperature of the hot object. If the temperature of the room is 10 Celsius, so Ts is 10 Celsius, find the time. You want to find the time T needed to cool the object from 80 Celsius to 30 Celsius and then 50 Celsius to 30 Celsius. First of all, you have the Ts is equal to 10 Celsius, and then the initial temperature T naught is 80 Celsius. Then you know that using Newton's law of cooling, dt over dt equal to negative k bracket T minus Ts. Then using separable techniques, you integrate dt over T minus Ts dt equal to negative integral k dt. Then you get, this is ln T minus Ts equal to negative kt plus c. And then T minus Ts equal to exponent negative kt plus c, or equal to A exponent negative kt. Plug in Ts, the surrounding temperature, which is 10. So you have T minus 10 equal to A exponent negative kt. And when T equal to 0, mean the initial temperature is 80 Celsius. So plug in 80 here. So 80 minus 10 equal to A, because when T 0, T 0, you have exponent 0, which is 1. So A, and then the left side plug in the initial temperature is 80. So 80 minus 10, you have 70. So A equal to 70. That's why you have actually the temperature of the hot object is actually T. The minus 10 you may bring to right hand side. So T is actually equal to 10 plus 70 exponent negative kt. Notice for Newton's law of cooling, to find the time T, you must find the what is the value of the k? What's the value of the k? So now, how to find what's the value of the k? We have the information, okay? Find the time needed to cool the object from 80 Celsius to 30 Celsius. Okay. So when 20 minutes equal to 50. Okay, they have the information. It takes 20 minutes to cool an object from 80 Celsius to 50 Celsius. So plug in the first information here. T equal to 20. Then the temperature will become 50 into this equation. So when the time is 20 minutes, after 20 minutes, the temperature of the hot object become 50. So I put it 50 minus 10 equal to 70 exponent negative k 20. And plug in here. After 20 minutes, the temperature become 50. So we have 50 minus 10 equal to 70 exponent negative k 20. So 50 minus 10 you have 40 equal to 70 exponent negative k, exponent negative 20k. Then you can find the k from here. So notice if the equation here, the k, as I said, if the Newton law of cooling, you use dt equal to negative k. After you calculate, the k will be positive value. Here, positive value. Okay, so you calculate the k. So you got 40 equal 70 exponent negative 20k. Okay. So means it brings the here this one to here. Cannot insert. So you have a 40 divide 70 or 4 over 7 equal to exponent negative 20k. Exponent negative 20k. To get the k, you take ln at both hand side. That's why I got ln 4 over 7. Okay, ln e will get will be negative 20k. Okay, ln e you get 1. So this is negative 20k. Negative 20k equal to ln 4 over 7. So k is actually equal to ln 4 over 7 divided by negative 20. What you get is 0.02798. So now you have the k value. You obtain the k value already. Then the question A, you want to find time t to cool from 80 to 30. Okay, after you obtain the k value, now you want to find what is t when the temperature become 30. Temperature become 30. Then you plug in temperature 30. Because you have the k value already, you have k value. Then you plug in the temperature now is 30, and you know the k value, then you can find the time t. So from t minus 10 equal to 70 exponent negative kt here, right? T minus temperature minus 10 equal to 70 exponent negative kt. Exponent negative kt where the k value is here. Then when temperature is 30, So 30 minus 10 equals 20 equals 70 exponent negative kt. Where the k value you know already, then you can find the time t. So again, this will become 2 over 7. 2 over 7 equal exponent negative kt. Okay, taking ln at both hand side, you get ln 2 over 7 equal to negative kt, where the k value you know already. Okay, this is your k value. Then you can find your time t. So the time t will be ln 2 over 7 divided by negative k. Let me show you how to get this value. The ln you got ln 2 over 7 divide by negative k. So negative k, the k value, if you want exact, then better you put it this one. Divide by negative, okay? So negative, negative, that's why this will become positive. So the k is actually, you have ln 4 over 7 divided by 20. So again, to put it ln 4 over 7, this one, divide by 20, this one, it become, okay, divide, mean divide by negative k, so this will become times 20. So you get the value is 44.77 true minutes. Okay, so this is the question A. Question A. The time needed to cool the object from 80 Celsius to 30 is actually so what's that? 44.772. This one 44.772. 44, okay, 0.772. This is from 80 to 30. In 80 Celsius, okay, and we know 80 Celsius to 50 Celsius. From 80 Celsius to 50 Celsius, it takes 20 minutes. 20 minutes, huh? And then from 80 to 30, yeah? Okay, 80 to 30 is actually takes the whole thing here. 80 to 30, it takes 44.772 minutes. Hence, okay, what is the time needed to cool the object from 50 to 30? So 50 to 30, of course, it takes 44.772 minus 20. So mean it will be, it takes 24.772 minutes. That is called question B. Okay, so I revise one more time. Okay, for Newton's law of cooling, capital T is the temperature. dT over dt is proportional to the difference of the temperature of the hot object with its surrounding temperature. To change the proportional symbol to equal, okay, because since the temperature is decreasing, we put the equal to negative K. But if you see some of the formula, they put positive K, also doesn't matter. Because if negative K, when you calculate later on, the K value will give you positive value. If the equation equal to positive K, and when you calculate K will give you negative value. Then we use K separable technique to find the temperature of the hot object. Ln dt over T minus Ts equal to negative integral K dt. And then, so you get ln T minus Ts equal to negative Kt plus C. So T minus Ts is exponent negative Kt plus C, breaks your exponent, become exponent negative Kt multiply exponent C. Assume exponent C is only constant, is a constant. Let's change it to A. So T minus Ts equal to A exponent negative Kt. When you plug in the initial condition, means when T equal to time T equal to 0, you have the initial temperature is T naught, then you can find the A. Because when time T 0, this term become 1. So 1A equal, you know the surrounding temperature is a constant, you know the initial temperature, then you can obtain the A. Okay, after you find the A, you have like here, where the Ts is a constant value. So the temperature of a hot object, this is temperature, is equal to the surrounding temperature plus the difference of the initial temperature with the surrounding temperature multiply exponent negative Kt. Negative Kt. So in this case, you can find two things. It's either you want to find the time needed to cool that hot object from the initial temperature to a certain temperature, or you want to, given the time T, given the certain time, you want to find what is the temperature. So mean from Newton's law of cooling, you can find two things. It's either given time T, then you find the temperature. Given a certain period of time T, you find okay, what is the temperature of that hot object at certain time T. Or, given the last temperature, you can find the time needed to cool that hot object. So to do that two things, first of all, you must find the K. To find the K, they must give you some information. For example, example 1. It takes 20 minutes to cool an hot object from 80 Celsius to 50 Celsius. Because you plug in 80, you know the surrounding temperature. Okay, you plug in, okay, it means 80, this 80 is actually the T naught. From here, T equal to Ts plus T naught minus Ts exponent negative Kt. You know the time T is 20, this one you know. Okay, you know the initial temperature, T naught, which is 80. You know 80. You know the surrounding temperature is 10. You know this thing, right? Exponent negative 20 K. You know the temperature. The last temperature is 50. So Ts I bring here minus 10. Right. Then you can find the K. Right. So after you obtain the K, it's either the question wanted to find the time T, or they want to find the last temperature of the hot object. This is a K. After we obtain the K, This question, they want to find the time t. So if they want to find the time t, they must give you the last temperature. Substitute the last temperature, you know the Ts, you know the T naughts, Ts known, you know the K, then you can find the time t. Let's look at another exercise. You have a cup of coffee is 90 Celsius when freshly poured. So means this is T naughts. After 2 minutes being served in the room at 27 Celsius, the coffee has cooled to 75. Okay, this information is needed for you to find the value of K. By Newton's cooling law, the rate of change of temperature is stated by the differential equation as dt equal to negative K bracket T minus Ts, where cap T is the temperature of the coffee and Ts is the temperature of the room. Find the temperature Tt and the time t at which the coffee has cooled to 50 Celsius. Okay, then from here, solve it using separable techniques. As just now, you get T minus Ts equal to A exponent negative KT. Put in the first sentence there so that you can find the K. Then put in the T naught is before that you must find the value of K by plug in the initial temperature and the room temperature. So initial temperature is 70, Ts is 27. From this one, plug in the Ts is 27. So when T equal to 0, the initial temperature is 90. T0 initial, this one is from here. Plug in Ts, so T minus 27 equal to exponent A exponent negative KT. You must find the constant A first by plug in the initial condition T0. Okay, exponent 0 you have 1, so you have right side is equal to A. So plug in the initial temperature is 90. So 90 minus 27 is, so A equal to 63. Hence you get T minus 27 equal to 63 exponent negative KT. Okay, this is actually general solution. This is particular solution. Okay, before you can proceed to anything, you must find the constant K so that you can find either time t or the last temperature. To find the constant K, you need to plug in this information. After 2 minutes being served in the room at 27 Celsius, the coffee has cooled to 75 Celsius. Then you want to find K, right? K. Then you have the T is 2, temperature is 75. Plug in there, then you can find the K. Plug in into your particular solution, then you can find the K. When T equal to, plug in here, the temperature, okay, the coffee cooled to 75 Celsius. Okay. So plug in after T, okay, time is 2 minutes, the coffee cool down to 75 Celsius. So 75 minus 27 equal to 63 exponent negative, okay, exponent negative 2K. So 75 minus 27 got 48 equal to 63 exponent negative 2K. So taking ln at both hand side, so you have negative 2K equal to ln 48 divided by 63. So K is 0.1360. You plug in K. Here. So therefore, this is actually T T minus 27 equal to 63 exponent. Okay, this one is already, sorry, not in here. Plug in K back here. T minus 27 equal to 63 exponent negative. Okay, this is a K value, this is the T. Okay, now what the question want? Find temperature. This case they want to find temperature. If they want to find temperature, they must give you the time T. Find temperature and the time T at which the coffee has cooled to 50. Okay, the temperature is actually okay, so we find the time T first, which the coffee has cooled to 50. We find this one first. Okay, what's the time T at which the coffee has cooled to 50? So plug in temperature is 50 to the particular solution with the K value. So you got 50 minus 27 equal to 63 exponent negative 0.1360 T. So 50 minus 27, you got 23 equal to 63 exponent negative 0.1360 T. Then taking ln at both hand side, you get negative 0.1360 T equal to ln 23 over 63. Then you can find the T is 7.4091 minutes. So this is the time T. Find the temperature TT is actually your temperature is here. Find the temperature TT. This is the solution. T minus 27 equal to 63 exponent negative 0.1360 T. Okay, so I repeat, this is a Newton law of cooling. Newton law of cooling, you can solve it using separable technique. You obtain here. To find the A, first step, after you solve it using separable technique, to find the A, you must plug in the initial temperature. So, okay, in this case, initial temperature is 90. So after you plug in the surrounding temperature 27, and then when time T equal to 0, exponent 0 is 1. So you have A equal to the difference of initial temperature with surrounding temperature. So it obtains the A. Okay. And then to proceed to find the time needed to cool down that hot object, or time needed to cool down a hot object to a certain temperature, or given a certain time T, you want to find what is the temperature of the hot object, you must find the K. What's the K value? Okay, means the problem of Newton cooling law, first of all, solve it using separable technique. You obtain here the general, after plug in the surrounding temperature, you obtain general solution. After you solve using separable technique, you obtain general solution. After you plug in the initial condition, initial temperature, you obtain particular solution. And then you need to find the constant K first before you proceed to find time needed to cool down the hot object to a certain temperature, or given the last temperature, you need to find what is the time needed. You have either two things, either you find time T or temperature, but you must find the value of K first. To find the value of K, they must give you some information. For example, this one, it takes 2 minutes. You got T. You got the last K temperature to 75. Then you can find the K. So that is the find the temperature TT. So the temperature TT means you must obtain the A value. Okay, of course, from particular solution, you find the value of K. So that is a TT. So in this case, your TT is actually this one, temperature TT. T minus 27 equal to 63 exponent negative 0.1360 T. So this is a solution for the temperature TT. Okay, and the second part, okay, and the time T at which the coffee has cooled to 50 Celsius. Okay, you want to find time T. Okay, after you plug in the K value, you got the last temperature is 50. So you put in the last temperature. Yeah. You already know the K value, you put in the last temperature 50, then you can find the time T. Okay. So with this, thank you for your attention.